Hi, welcome to this video. This is asked for by Antonia, and she wants a video done on mass spectrometry. Okay, so let's write this down. Mass spectrometry. Now, it's quite a big topic, so I don't know how far we get on this today. Okay, I don't want the video to be an hour long. 10 minutes or 15 minutes, that's well long enough. All right, let's have a look at the machine itself. Let's have a look at a mass spectra machine. Mass spectrometer. Machine. What does the machine look like? Okay, now I'm going to draw it very schematically. Okay, so you have first of all, you have the vaporization chamber. Okay, so you put your stuff in here and the stuff is vaporized. Okay, all right, so the first thing that happens is vaporization. Vaporization. Okay, that's if it's a liquid or a solid, it gets vaporized. Then, next thing it goes through is the electron gun. Electrons are fired at it. There you go, bang and bang. And what happens here is the sample lose electrons and they become ions. So this is called the ionization chamber. Okay, so we vaporize it, then we ionize it. Now they're ionized, they're ions, aren't they? So they're charged. Okay, so after we've charged them, we can bring them into the machine itself. Okay, and how do we drag positive and negative things in? We drag them into the machine using an electric field. So this is an electric field, and it zaps the ions into the machine. Okay, and they zoom along in the machine. All right, and then we pass the ions through a magnetic field. So this thing represents a magnetic field. Okay, and the ions come along. Let me do my ions. And they come along and they're bent in the magnetic field. Okay, and they're bent and they're forced to land on some sort of recorder. And because they're charged, they create a tiny, tiny current. Okay, so these are the charged ions being bent. Charged ions. All right. Now, what happens to the uncharged ions? Well, to be honest with you, they stay in here. Okay. If they don't get a charge, they won't move into the machine because they haven't got they haven't got an electric field, have they? So they'll stay here. The neutral particles will tend to stay here. All right, and they won't go into the recorder. What happens in my electric field, sorry, in my ionization chamber as well? Well, a couple of things. They get ionized, but also in this chamber here, the ionization chamber, we also break them apart and we say they fragment here. Okay, and when they fragment, let's have a look at something simple. Let's have a look at this guy. This is ethane. Okay, and let's smash it in the middle, smash it here. Okay, now if you can just smash it, all right, like that, you'll end up with, and you can count the electrons yourself, you'll end up with 2 bits. Okay, and let's pretend there's an electron there and an electron there. So there's 2 radicals there. But don't forget, one of the radicals has been smashed apart by the electron. And so this electron on this radical there will have been shot off. Okay, so this will be a positively charged thing. So when you split something up, you end up with an ion and a free radical. Okay, so the free radical is neutral. And the free radical doesn't go into the machine, so the free radicals hang around this ionization chamber. Okay, free radical. Because they're not charged. So this splits up into 2 things. The thing on the left goes into the machine and it will be recorded, and the thing on the right doesn't go anywhere, it's a free radical. So this is an important point. When you show your peaks, you should always show them charged. So this is how we do it. That's the methyl peak. Okay, and we show it charged because it is charged. It's not the radical, it's the one that's charged. Anyway, so there you go. So the bits and pieces go into the recorder down here. All right, and let's pretend I have a heavier fragment. Well, the heavier fragment, it won't get bent as much and it will miss the recorder, so we won't record that. And the lighter fragments will be bent too much, and we'll miss those. So what we do is we move the recorder this way and this way to capture the different fragments. Okay, actually I don't think they do that. They don't move the recorder, they change the magnetic field strength. Okay, but it's the same thing really, isn't it? So they change the magnetic field strength in here, and they focus different streams onto the recorder. Okay, and from that you can tell their masses. And from this, we get what we call a mass spectrum. This is a mass spectrum, okay? And this is abundance on this side. And down this side, it's the mass over charge ratio, okay? So the red peak, say we'll get a peak here, the white peak here, and the green peak maybe here. Okay, now mass, what's the mass over charge is m over E. Okay, now E 99.99999% of the time is 1, isn't it? Plus 1. So this is the mass over plus 1. So it's effectively just the mass. Okay, and we get a mass spectrum here. Even though it's called the m over E ratio, we just get it's the mass. This is basically just the mass. Okay, so that's the setup. I hope that makes sense. Okay, let's go on to the next bit of the video. Whoops, wrong one. All right, I hope this is making sense. Now, let's have a look. Let's have a look at a mass spectrum. Oh, that's quite good, actually. So this is abundance. And this is m over E, mass over charge. All right, and then we get some peaks. So let's have a look at a typical molecule. Let's have a look at this guy. Let's have a look at methanol. This is methanol. So where's methanol going to be smashed up into? Well, you could imagine, and I'm ignoring the free radicals here, eh? Because they don't make a mark on this thing. You can imagine a methanol molecule goes through the whole machine, CH3, CH2, OH, and it goes through as the molecule, just without an electron. Okay, there you go. And the mass over charge ratio for this thing is 46. So we'll get a peak at, there it is, 46. Okay, now if it goes through the whole machine without losing any mass, just an electron, the peak is known as the molecular ion peak. This is the molecular ion peak, and it's given the symbol M+. Okay, that's the molecular ion peak. It can, let's say, smash it up. A very common place to smash it up is here. So we'll get a fragment here. We'll get a CH3 fragment, which is a mass over charge ratio of 15. That's a very common peak as well. And we'll get this funny thing, CH2OH. So what's that? That's going to be 31, isn't it? I think. Okay, and so we'll get an m over E of 31 for this peak. So let's fill them in. Oh, I'm not going to do this properly. I'm just going to say this is 15. We'll get a peak there for this one. And we'll get a peak at 31. I'm putting it here. Let's put it here. 31 for this one. Okay, how else might it smash up? Commonly with alcohols, they smash off here. All right, so we'll get the CH3, CH2, very common peak, and this is m over E equals 29, I think. I'm not even going to work it out because I'm so sure it is 29. And this one is, the OH peak is 17. Okay, so you'll get a peak at 17. Let's see here. I don't know. Let's have a look here. This is 17. And your off very common peak is one at 29. Okay, so there you go. So what a professional would do, they'd look at these peaks, and they're very experienced, and they'd look at these peaks and say, oh yeah, that's a CH3 peak, that's a OH peak, this is a CH2 CH3 peak, this is a CH2 OH peak, and this is the molecular ion peak. Okay, and they'll figure out it's ethanol. All right, so that's how they do it. All right, so that's the basis of mass spectrometry. And these things, by the way, these are known as fragments. They're not the whole molecule, are they? They're just fragments, and this is the molecular iron peak. So that's that bit, okay. And we want them to fragment, because if all we got was the molecular iron peak, you wouldn't find structure in the molecule. All right. So the molecular iron peak is useful, but the fragments are very useful as well. Okay, so let's have a look at some examples of how this works. Hope the video is not going for too long. All right, so let's have a look at a couple of things that we can do with this. The first one is we can find out the number of carbon atoms in the molecule. Okay, now this is done with a trick of statistics. Carbon comes in two flavors, or two main flavors. There's carbon 12 and carbon 13. It also comes in carbon 14, okay, but we're not going to worry about that. Carbon 12 is like 98, or what is it, 1.1, so it's 98.9%, is that? 1.1% is carbon 13, and carbon 14 is so small, the percentages, we call it trace. Okay, so obviously there is some of this, but it's trace. Now you're thinking, oh, but how can that be? Because 98.9 plus 1.1 equals 100. Obviously, these aren't exact numbers, but you do get some carbon 14. But it's basically just these two. Okay, so let's have a look. If I've got a methane molecule and I've got another methane molecule. Okay, this one, the one on the left, is carbon 12. One on the right is carbon 13. Okay, now both of these molecules exist, they're hanging around, all right, but 99 point, sorry, that's wrong. Well, I'm going to call it, 99 for now. 99% of methane is going to be this type, and 1% is going to be this type, about, okay? So if I put this on if I put methane through my mass spectrometry machine, we'd have abundance on the left, and this is our M over E. We'd get, well, the mass of this is going to be, 16. M over E is 16 for this one, but the M over E for this one is 17 because the higher isotope is being looked at. So we'll get two peaks here. We'll get a peak at 16 and we'll get a peak at 17. Now, the peak at 16 is going to be about, now I'm going to use the proper number, 98.9% about, isn't it? And the peak at 17 is going to be about 1.1%. Okay, now there you go. That's what you'll get. You'll just get that as a mass spectrum. So there. Now I know we're looking at methane here, but if we get the M plus 1, oh, by the way, this is the molecular iron peak, as we talked about last one, the one at 16. And the one at 17 is called the M plus 1 peak. Okay, and there it is. And what is responsible for the M plus 1 peak? The presence of carbon 13, the presence of this stuff in the molecule. Okay, so now, what are the chances of a carbon 13 being in the molecule? They're about 1%, 1.1%. Okay, and what is the percentage of carbon 12 being in it? About 99%. Okay, so there you go. All right, so we'll get this particular ratio between the M plus 1 and the M peak. But now let's change it to a bit more of a longer molecule. Now let's have a look at propane now. There's a propane, and there's a propane. Two propanes. And let's say the one on the left has a 12, and a 12 in, and this is a 12, and a 12, and this is a 13. Now you can get that, or you can get C, C, C. Okay, and now this could be a 12. This middle one could be a 13, and this one could be a 12. So there's already two chances now of having a carbon 13 in the molecule. And now let's do the last one. 1, 2, 3. First one could be a carbon 13. This could be a 12, and this could be a 12. So all of these three will give you, what's propane? 1, 2, 3, 36, 37, 38, 39, 40, 41, 42, 43, 44. This has a mass of 44, and over E of 44. All of these three will give a mass overcharge of 45. Okay, so now, whereas in the first place, the chances of 12, 12, 12 is whatever percentage that is. Now, you have a 1.1% chance of this one. You have a 1.1% chance of this one, and you have a 1.1% chance of this one. So the chances of there being a carbon-13 in the molecule is now not 1.1, it rises proportionately as the number of carbon atoms increases. So now it's 3.3% chance of them being in this, and this will go down proportionately. This will be 96.7% now. Okay? All right, so purely because the number of carbon atoms increases, there's more chance of there being a carbon-13 in, okay? And as the number of carbon atoms increases, proportionately, the chances of a carbon-13 in the molecule increases. And it is proportional. So if you double the number of carbon atoms, you'll double the chance, okay? Now, where are we? So this is how we find out the number of carbon atoms. Now we package this all up into a nice formula, and we say the height of the m+1 peak divided by the height of the m peak times 100. Now that will give you the percentage of the m+1 into the m. And if it's, roughly speaking, it's 1.1%. That should be, if there's one carbon in there. So we divide it all by 1.1, which is this number up here. Let me do this nicely. This number up here, okay, to give you a nice integer number. Okay, so that's the point of the 1.1 there. So, excuse me. So as the number of carbons increases, the chances of there being a carbon-13 in the molecule increases. Now, some of you will say, well, what about the chance of there being 2 carbon-13s in the molecule? All right, or even 3. Now, this obviously will happen, but the chances of there being 2 carbon isotopes, 2 carbon-13 isotopes in the molecule, is very small. All right, and the chance of there being 3 in the molecule is even smaller still. So we don't even consider those possibilities. We only consider the possibility of there being 1 carbon-13 in the molecule. Okay, so that's why we have an m+1 peak. Okay, so we use this here to find out the number of carbons in the molecule. It's the height of the m+1 peak divided by the height of the m peak. That will give you 1.1 for every carbon in it, yeah? Times that by the number of carbons in it, and divide by 1.1, because that's the naturally occurring ratio, and that will cancel with that, and it will give you the number of carbons in the molecule. Okay, let me see, how long has this video been going? I don't want to go too long, because there's something else I want to talk about now. All right, let me shoot on now, quickly. That's the carbon-13 aspect, so I hope that helps. Now, we're going to look at the, let me do that a bit nicer. All right, now we're going to look at the possibility of there being halogens in the compound. Okay, so we've done the m+1 peak, and this is because of the carbon-13. All right, but now, because of a trick of nature, then that's all it is. Chlorine here, my friend chlorine, comes in 2 flavors. Okay, bromine comes in 2 flavors as well. Okay, chlorine comes in 35 and 37, but bromine comes in 79 and 81. Now, the trick of nature, as I said, is the difference between 35 and 37, and the difference between 79 and 81 is 2. Okay, and that's just fluke. You know, there's nothing magical about that. They happen to be 2. So if you have a molecule here, let's have a molecule. Let's have a simple one to start with, and another molecule here. I hope I'm not going into too much detail here for you, or I hope I'm not going too slow, which is very possible. But these videos you're not supposed to watch them with a pen in one hand and writing down your notes. You're supposed to watch these with a cup of tea, sort of on a nice Sunday morning. So let's pretend that everything's normal here. This is a 12 and this is a 12. And we're not looking at carbon-13s yet. We'll maybe look at them later. All right, so this chlorine is 35 and this chlorine is 37. and this bromine is 79, and this bromine is 81. Okay, so what's the mass of this? This is 35, 47, 50, I think, if I'm not mistaken. The mass of this is 50, so is that right? 35, 36, 37, 38, 39, 40, yeah. And therefore the mass of this is going to be 52. All right, and the difference there is 2 because of the differences in chlorines. Now, here we go. 79, 80, 81, 82, 92, 94. I think the mass over this one is 94, and the mass over charge of this one is going to be 96. That's going to be a 2 as well. Okay, so if we were to plot, oh sorry, if we did the mass spectrum of these two, okay, I'm drawing tiny ones here. What would we see? We'd see a peak at 50 and a peak at 52. We'd see a peak here at 94 and a peak here at 96. And this one would be whatever height, and this height, and this height, and this height. Okay, and now we would get the n+2 peak. And this is the n+2 peak. Okay, the other one, this one here is the n peak. And this is the n peak, molecular ion peak. Okay, so whatever, if there's a chlorine or a bromine in it, you're going to get an n+2 peak. So the n+2 peak in mass spectrometry is because of the presence of chlorine or bromine. Now, obviously, iodine could be there as well, couldn't it? But that doesn't have an n+2 peak, and that's not on the course. So we're only looking at what we're doing on the course. So you have an n+1 peak, is carbon-13. n+2 peak is the presence of chlorine or bromine. Now, so you'll get a peak at M, and you'll get an n+2 peak. You'll get a peak at M, and you'll get an n+2 peak at n+2 peak. So that will tell you there's a halogen present. And now what halogen is present? Okay, let's have a look at this. All right, so what halogen is present? Because you get an n+2 peak for both of them. So let's have a look at a nice simple one. There we go. There's chlorine, and there's going to be another chlorine here. Okay, now the ratio, the ratio, I guess, between carbon-35 and carbon-37 is there's 75% of these and there's 25% of these, or 3:1. Okay, so 35 and 37. So if I were to plot these things on a mass spectrum, I get 50 and 52. Okay, the 50 peak would be 3 times as high as the 52 peak. So from the ratio of the peaks, 3:1, I can deduce that the halogen is chlorine. From the ratio. Okay, are we good there? Yeah, I hope we're good. Okay, so it's from the ratio we get chlorine. There's an n peak and the n+2 peak. And from the ratio of these guys, we can tell it's chlorine. Now, what if it's bromine? Well, the ratio is going to be different. Get rid of that, get rid of that, get rid of all of this rubbish. Okay, so let's pretend we had a bromine. And a bromine. And this one is 79, this one is 81. Naturally occurring bromine, Br to Br. And this one is 79, and this one is 81. Naturally occurring bromine is 1:1. Okay, so I'll get, now let's change my graph down here. Get rid of all this rubbish. And let's extend this a little bit. Okay, so we get a peak there and a peak here. This one is, what was it last time? 94, I think, 96. This one will be a certain height, and this one will be the same height. So the ratio here is going to be 1:1. So if the ratio is 1:1 of the M peak to the n+2 peak, your halogen, we can deduce, is bromine. Okay. Now, there you go. That's it. Very simple. Now, I wasn't going to say this, but I will say this just in case. if you have, let's have a look, if you have two halogens. So if you got, sorry, let me start again. If you've got one halogen in the compound, you'll get an N peak and an N plus 2 peak. If you have two halogens, okay, oopsie daisy, let's do this. Let's start again with this, and I'll tell you, I don't want to spend long on this because it's quite unusual they ask this, but they do sometimes. Okay, so let's have a look at this possibility. Okay, oops, I messed it up already. Oop, wrong one. All right, let's put two chlorines on. Now we have two halogens on the molecule. All right. Now what can I get here? Well, this is a, let's say 35 and a 35. And this one could be a 35 and a 37. Oh gosh, and I've got to draw another one now, haven't I? And you can also get, whoops, you see I'm rushing now. And when I rush, it always goes wrong. You can always also get a 37 and a 35, can't you? They're the possibilities. Oh, and there's one more. Gosh, this is why I didn't want to do this. It's much easier in class to do this stuff with people shouting at me, telling me I've got something wrong. All right, so let's do the masses of these. What are the M over E's? Well, the M over E of this one is that's 70, 82, 83, 84. The M over E of this one is going to be two more, 86. The M over E of this one is also going to be 86. And the M over E of this one is going to be 88. Okay, so now if we plotted abundance over M over E, we're going to get 1, 2, 3, 4. That's 5. Let's start there. This one's 84, 85, 86, 87, 88. So you're going to get a peak at 84 for this one. You're going to get a peak at 86 for this one. You're going to get a peak at 86 for this one. And you're going to get a peak at 88 for this one. So when there's two halogens in the molecule, okay, we have an M peak, we have an N plus 2 peak, and we have an N plus 4 peak. Because there's two halogens. This is the M peak, N plus 2, and N plus 4. Now, what are the relative heights? I've drawn them as 1 to 1 to 1, but they're not as simple as that. Okay, now, what are the chances of this first molecule? Right, let's say Cl35 and Cl35. That's one chance. Cl35 and a Cl37. That's the second chance. Cl37 and a Cl35. That's the third one. And a Cl37 and a Cl37. Oh, look at that! These are the four types of molecule you can get. Okay, so Cl35 and Cl5. Well, the chances of a Cl35 is 3, and the chances of a Cl35 is 3. Remember, it's 3 to 1 for chlorine, so it's 3. Okay, 35 is 3, 37 is 1, the chance is 1. Chance of a 37 is 1, chance of a 35 is 3. Chance of a 37 is 1, chance of another 37 is 1. So let's do this. This is 9, this is 3, this is 3, and this is 1. These two are the same mass, though, so this is up as 6. So we get a ratio of 9 to 6 to 1. Ratio of 9 to 6 to 1. Okay, this is if there are two chlorines in it. So if there's one chlorine, it's 3 to 1. If there's two, you get a 9 to 6 to 1. Okay, I hope you mathematicians are okay with that. If we do the same with bromine, I'm not going to go through all of this with bromine, but I'm not going to draw the picture. You can get a 79 and a 79. You can get a 79 and you can get an 81. You can get an 81, whoops, and you can get a 79, and you can get an 81, and you can get an, that's gone wrong. You can get an 81. Okay, now, if you remember, Bromine is 1 to 1. So chances of that is 1 times 1. Chance of that is 1 times 1. Chance of that is 1 times 1. Chance of that is 1 times 1. But these two are the same mass, so this is 2. So for bromine, if there's one bromine, you get a ratio of 1 to 1. This is chlorine. And this one, different color, is bromine. There's 2 in the molecule. All right. If there's 1 in the molecule, it's 1 to 1. If there's 2 in the molecule, the ratio is 1 to 2 to 1. So you'll see this, okay, rather than with the bromine, the chlorine, this. Oh, that's not quite right, is it? There. Okay, I hope that makes sense. Now this is the derivation of the M peak, the M plus 1 peak because of the carbon-13, M plus 2 peak because of 1 halogen in the compound, and the M plus 4 peak if there are 2 halogens in the compound. All right, hope that makes sense. I'm getting out of here now because this is long enough.